Good afternoon and welcome. Yes, your hair is correct. Welcome to the 7th episode already of Meet the Oracle Masters, the online series. Today is Chris Saxon with his talk on how to read an execution plan. If you have any questions, feel free to use the chat if you want us or other people to answer them. If you want Chris to answer them, please use the Q&A for that. And now over to you, Chris. Enjoy.
Alrighty then, thanks Patrick. Just give me a second to get my screen up. So hopefully you've got my screen up there now. And
yes,
let's get going. All right then. So SQL is really cool. It's awesome. The great power of it is its declarative nature. You tell the database the result you want, and it figures out the fastest way to do it. But this brings about an interesting problem. If the database figures out how to execute your statement and the query is too slow, how the heck do you go about making it faster, right? It's one of those perplexing problems. And when you start learning about this, you'll probably ask people and say, well, what do I do to help tune my SQL statement? And you'll ask some wise, learned people, and they'll say, look at the execution plan. And you say, all right, I've looked at some execution plans, but how the heck does this help me, right? I've looked at some of these, they just don't make any sense. So thing to note here is that an execution plan, or the plan, is like the optimizer's driving directions. So just like if you're going to go on a journey, you'll get some mapping software and it will tell you to take a route. So for example, back in the good old days when we actually used to see each other in person and travel to places, if I was doing this event, I'd probably do something like this. I'd get in the car or take the train to Bristol Airport, fly to Amsterdam, and then again get the car or train down to actually see you and present this in person. So that's what things look like in the physical world for following a route of directions. But with an execution plan, you've got something like this. You've got a bunch of tables listed, maybe some indexes and some joins. And you probably looked at them and go, yeah, they don't look like driving directions to me, right? How the heck am I supposed to follow those? So that's what we're going to look at in this session. We'll look at how you can essentially draw the arrows on the map there of the plan, and then we'll follow to look at some common problems or things to look for in execution plans and ways you can address those to hopefully make your SQL statement a bit faster. So standard disclaimer, as we always have here in Oracle, don't believe anything I say. Okay, let's get started properly. So we've got our little simple plan. And what we want to do is draw those arrows showing the route that we take through this. So how do we go about doing that? Well, the first thing to note is that an execution plan is like a tree. Not like a physical tree, but like a data tree. So each operation has at most one parent and can have multiple children. And the parent-child relationship is defined by the indentation, or at least in plans that look at like this, you get from DBMS X plan, the indentation determines that parent-child relationship. So if we look at this hash join here, then its parent operation is the first operation above it that is indented to the left. So that's this select operation here. Its children are those operations that are below it that are indented to the right. So that's the two full scans from those two tables. So the hash join has the parent of the select statement and the children of those full scans. And this indentation is really important and useful to figure out that relationship. Which is why it's really frustrating when someone sends a plan like this, where everything is just kind of left justified and lined up along here. Simple two-table plan, we could probably riddle out what's supposed to go on here, but you quite often you can get plans which are like 20, 30, 40 lines long. Figuring out the parent-child relationship when everything's just perfectly lined up along the left here, really, really tricky. So if you're sending a plan to someone else and you want some help from them, please make sure you've got your indentation right, okay? Otherwise it just becomes a nightmare to figure out what's going on. So we've got our plan, the select operation is the root, we got our full scans of the colors and bricks table, they're the leaves. So that gives a tree that looks a little bit like this. So what route do we take through this? How do we start? Well, what we do, start at the top, start with the select, and from there we go down to the first unvisited leaf. So this is going to be the topmost table in the plan. Once we've got there, the database will read the rows out of that table or index or whatever it is. It'll then pass the rows up to its parent. So we go down to the first unvisited leaf, back up to the parent. From there, we go, okay, what's the next unvisited leaf? Repeat the process. Look for the next unvisited leaf. Once we've read the rows from that, go back up to its parent and keep recursively doing this. If you're familiar with various data structure algorithms or tree traversal ones, this is just a depth-first search of that tree. So let's see how it works with this little simple plan. We'll start nice and easy. We'll build it up, get more complicated as we go along. First thing we're going to do here, start with that select operation. Travel down to the first unvisited leaf. So this is the topmost table in the plan with no children. So that's the full scan of our colors table here. We'll read the rows out of that, pass them up to the hash join. It will then go, okay, what's the next unvisited leaf here? Well, that's the bricks table. We'll get the rows from that, read them, pass them up to the hash join. Nothing left to do here. We've read all the data sources, so we'll return, join the rows, return them to the select statement at the top. Pretty simple to start with. Let's level it up a little bit. Okay, let's go for a 4-table join. Looks a little bit more complicated, but the process here is exactly the same. Start with that select statement, work our way down to the first leaf, that's our colors table, read the rows out of that, pass them to the hash join, go for the next leaf, get the toys, pass them up to the hash join. Now at this point, there are no other children for that hash join. So we skip the next unvisited leaf, just go straight up to its parent. That's this hash join. Look for the next unvisited leaf of this. That's the full scan of the pens table. And we'll continue winding our way through the table like this. So we get this kind of little funky back and forth through the execution plan. So this is a fairly straightforward, this is a basic just join all the tables together. Let's level it up again. We'll have the same 4 tables, but we'll do something subtly different with them. So we'll get a plan that looks a bit more like this. Okay, so start off the same. We'll start at the top, work our way down to the first leaf, colors table, read the rows out from that, and pass them to the hash join. From there, we've got to work down to the next leaf in the table. So that's all the way down to the bricks table. So these full scans are all children of that union all operation. So we'll work our way, read through them one by one. And if this is just a serial query, standard non-parallel one, the database will read them one after the other and pass them back up to the union all. If you're running the query in parallel, the database can actually read these tables at the same time. So if you're running with 3 parallel processes, you can start reading all 3 of them at exactly the same time. But in any case, the principle is the same. We read those rows, pass them up to the union all, which combines them into a single data set, pass those back up through the plan and work our way all the way up to the top again. So again, we just worked our way through. All right, let's level it up again and do something a little bit different this time. Okay, so we'll go back, and at first glance, this looks a lot simpler. But if you look carefully at this plan, you'll notice it's subtly different. There's something missing here. There's no join operation in this plan. So what's going on here? I've just got full scans of the 2 tables and a sort aggregate. I haven't actually joined them at all. So what kind of query would generate this kind of plan? Interesting. Well, this is a scalar subquery. So this is when you've got a select buried within the select clause of a query. Now, the thing to note here is the database processes the from clause before the select clause. So we get all the rows out of colors, and then for the rows we get, we then run the select clause, this scalar subquery. And if we look at the plan, that colors table, it's actually right down there at the bottom. Right? So this has broken my travel down until the topmost leaf in the plan rule a little bit, hasn't it? Okay. So how do we know we need to do this? Well, it's that we've got a scalar subquery. We're processing the select clause after the from. Also, we can see there's no actual join operation going on here. There's no hash join, nested loops, anything like that. Sign that something different is happening here. There is another clue, which we'll get to a bit later. So how do we follow the process here? Well, we start with the select. We go down to the first table in the from clause. That's actually this colors table. We'll read the rows out of that. Once we've got the rows, we can then start reading them out of the bricks table. So get the row, query the bricks table, return the results from that. Now, the key thing about this is this scalar subquery, we could end up running it many, many times, potentially up to once per row we get out of this source table. There are some optimizations in Oracle database, so it's not always that often, but worst case, every single row we get from colors, we might end up doing a full scan of the bricks table. Doesn't sound very good, right? We'll come back to how we might address that a little bit later. Okay, so we've seen ways how to draw the arrows. This is the route we follow through the plan. How does this help us make it faster, right? How does just having the arrows on this help in any way? We return back to like the driving directions or route directions in the real world. Got my map here with the arrow showing the route I'm following to get from my house to visit you in one day when we're allowed to see each other for real again. And I'm like, oh, this journey, it took me forever. I want to go faster. And I'm going like, come on, I want you to help me. How can I do this quicker? You're probably kind of like, well, I don't know, right? There's information you need to know about my journey to figure out whether or not there's better ways of doing it. Things like how far we've actually traveled. So that gives some idea of how long it's possible, how quickly it's possible to get here. Then you might look at how long it was estimated to take versus how long it actually took. Quite often you'll enter your route into some route planning software, and it'll give you 2 or 3 different choices with estimated times for each. Generally, you just choose the one that's the quickest, right? But what if that isn't the case? Let's say it's estimated to take about 5.5 hours, and my journey actually took me like 9 hours or more than 9 hours. So I probably chose the wrong route here. Or maybe there's a faster way of doing it, right? If you want to know why this took me so long to get from my house over to you in the Netherlands, ask Patrick, and he'll be able to tell you why this took so long last time. So finally, the other question is, what other routes could I have taken? Maybe instead of going to Bristol and flying from there, it would have been quicker for me to either go to London and fly from London, or fly to Rotterdam or something like that. Or maybe I could have driven all the way and got the ferry, or taken the Eurostar. What other routes are there available? How fast are they? And how do they compare to how long I actually took? So that's kind of questions we need to ask if you're trying to optimize a real world journey. Similar kind of questions you need to ask when you're trying to optimize the database journey, the database driving directions. So there's 4 kind of key questions I'm going to say you want to ask here. First thing is the row estimates. So when you submit the query, the database looks at the table statistics and information and asks, based on how many rows I think I'm going to get from these tables, this is how I'm going to access them and the order I'm going to join them. Provided the estimates for how many rows it thinks it's going to get is pretty close to the number of rows it actually gets from each table, then generally speaking, you've got a good plan. If, however, there's a big difference between them, we saw estimated 9.5 hours for my journey took me 5.5 hours for my journey took me 9 hours, would have been quicker to take a different route. If we're estimating 10 rows from a table and we get 10 million rows, yeah, maybe there's a better way we could have accessed our data, or joined the different order we could have joined the tables. So that's the first thing we look at. Are the row estimates accurate? Assuming they are, now we've kind of got a good plan. We need to ask is, how much work did we do? How much effort did we have to go to in order to actually get those rows? And the key thing you want to look at here is how much I/O did we do? So this is often referred to as consistent gets, logical I/O. That is, every time we access a database block. The more times we do that, all other things being equal, the slower the query is going to be. Any computer system, there's 2 key resources, CPU and disk. If your CPU U bound in the database is generally a good thing because you can scale fairly easily just by adding more compute capacity. If you're I/O bound, on the other hand, it's much harder to scale your database. So you generally want to keep your number of I/O requests low. So we want to look at that. So we figured out how much I/O we're doing, and we've kind of gone, oh, that's a lot of effort to read these rows. You're going to ask, well, how else can we read these rows? What are the other techniques or things can we do to reduce the I/O that we're doing? And then finally, of course, you want to look at how long it actually took, how long it took to process the query in total or individual steps here. Ultimately, the customer doesn't really care about these first three things. They don't care that you've got your stats exactly right, that the row estimates are perfect, and you tuned your I/O reads down from 1,000 to 10 or something like that. They care that the query execution time, the response time, has gone from 10 seconds down to 10 milliseconds, right? That's what they really care about. But when you're tuning your query, you actually want to focus on these first three things because those are the things you can really influence. Again, if we're looking at driving, let's say you're driving somewhere and you say, well, how can I reduce the time it takes to get to my destination? There's two basic things you can do. You can drive faster, or you can try and find a shorter route. You can't do taking 10 minutes less. You can do driving quicker or finding a shorter route. So if you manage to do those things, the consequence is you get there quicker. We reduce the time. Same with plan tuning. If we improve the row estimates so we get a better route through the plan, reduce the work that we're doing, possibly by creating better access methods, we can reduce the time it takes to execute the query and everything's good. But ultimately, like I say, how long it takes is the thing that really matters. Okay, so how do we get this information? Well, there's lots of ways you can do it. I really like the auto trace option in SQL Developer. It gives you a nice little graphical plan where you can expand and collapse things. But if you're asking for help from other people who you don't work with or you can't share your screen with, then DBMS Xplan is my preferred way. So we'll run it like this. We'll set server output off, run your query with the gather plan statistics hint. Very important, because without this, we just get the shape of the plan. We don't get details about how many rows we actually processed, how long it actually took. You need that hint, or there's in the session, you can alter statistics level to all, set that, run your query, afterwards call DBMS Xplan. There's various formats you can pass in here, but if you just use all stats, that can give you a whole bucket of information, and that will add some extra columns to your execution plan. Like I say, there's various ones it can add. Exactly which you'll get, it's quite smart. It only adds ones which are relevant to your query. For example, if you've got a query on partition tables, there will be some partitioning columns. If you've not, those partitioning columns won't appear. So you only get columns that actually have information that's relevant to your query. But there are 5 key columns which you'll basically always get, and that are these ones: starts, E rows, A rows, A time, and buffers. So what are they? What do they mean? So starts. How many times did we do this thing? Obviously, the more times we do something, the slower it's likely to be. E rows, estimated rows. How many rows did the optimizer think this operation would return? Okay, so if we've got full scan and it's a 10 billion row table, it's not going to estimate 10 billion rows, it's going to estimate how many rows we're going to fetch from that. If we've got a where clause, primary key lookup, so we get 1 row, it'll estimate 1 row. How many are we going to return from that operation, not what's the underlying total data set. And how does that compare to the A rows, the actual rows? How did these stack up? Are they broadly similar? Then we've got the A time, actual time, and that's here in hundreds of seconds. And finally, we've got the buffers, logical I/O. So this comprises 2 things: consistent gets and current mode gets. So all other things being equal, the query that does the fewest buffers, least I/O, logical I/O, will be the fastest. Not always true, but generally you want to make sure you reduce this as much as possible. Something else to mention here. These 3 columns on the left, starts, E rows, A rows. they are all specific to that individual operation. So we're saying this second line here, we did it once, optimizer estimated 68 rows, we actually got 56 rows. So they are specific to that operation. These two columns, A time and buffers, on the other hand, are cumulative. They are the total for that operation plus the sum of its children. So if we want to look at the total work done by this query, the total I/O, we don't sum up all of these to get a total of around 100 or so. No, we just look at the top line and say we did 24 logical I/Os in total, which took us around 10 milliseconds in total. To get the time and the buffers for an individual operation, you need to subtract off the values for its direct children. So you need to know what are the ones directly below this, so we can see how much work this individual operation actually did. So this is kind of the basics, and this is all we need to really know for most queries. Some other queries other information might be useful, but this is the core information you're going to use basically every single time. So let's look at some common problems you might encounter, or reasons the optimizer has chosen a bad plan, or things we can do to improve the plan. And we'll start with bad row estimates or incorrect row estimates. So got a plan like this, and if you look at this a minute or so, you might spot something a little bit dodgy here. Merge join Cartesian operation. That's a bad sign generally. Often it can be a sign that you've missed a join out of your query. Hopefully you're not doing that. You know, if you're using the ANSI style syntax, it's pretty tricky to do that by mistake. But it's possible you'll see this just because you've forgotten to join tables. But you can still see this even if you've got all your joins absolutely correct. And trust me, in this query, I've joined all the tables as I was supposed to. I haven't forgotten to do something or actually put in a cross join. So why? Why has the optimizer decided to go for a merge join Cartesian? Well, it's estimating you'll get one row out of the bricks table. And this is an interesting thing. If you are joining one row to another data set of basically any size, a merge join Cartesian can be the fastest way to do it. But this relies on there being exactly, or at most, one row from that first table. How many rows did we actually get out of this table? 24. Oh dear, that's not good. We're out by a factor of 24. So when there's a difference, an order of magnitude more difference between the estimated rows and the actual rows, it's a sign that something's probably not quite right, and maybe our stats are not what they should be. So the consequence of this is we get our 24 rows from our bricks table, we execute the other side of this join 24 times, okay? So we could end up doing whatever this thing is here a lot more times than we really wanted to. Also, this estimate error could propagate up through the plan, leading to other bad choices about join types. Okay, so we had one, clearly that was wrong. Let's look at this operation, this buffer sort. We're estimating 5 rows, we actually got 120. Now at first glance, again, this looks like the optimizer's just got it hideously, hideously wrong, right? There is a more than an order of magnitude difference between 5 and 120, isn't there? In fact, you know, there are difference between them is 24 times. There's a factor of 24 difference between them. Oh, hang on, 24. That's how many times we did this thing. That's how many times we executed this operation. So that's something you need to be aware of. When comparing the estimates to the actuals, you need to multiply it by the number of times it started. 5 24s is in fact 120, so the optimizer got this estimate bang on. First glance, it might look it's way out, but it is in fact bang on. Multiply the starts by the estimated number of rows. Going further on down the plan, we can see for this full scan as well, we're estimating 100 rows, but we just got 3. So we're out by a factor of over 30. Okay, so we've a couple of tables here where we've just got wildly, wildly incorrect stats for them. So this question, see who's paying attention. How would we fix this? You're going to be brave and put something chat and suggest how we would go about solving this? Any takers?
None yet.
No, none yet. No one's brave enough.
Here's one.
Statistics. Theo, yes, that's it.
Statistics stats, question mark. Wow.
Question mark. Yeah, so what we want to do is update the table statistics. We want to regather stats on the tables. So pretty straightforward here. We just do dbms stats, gather table stats. This updates the optimizer's information about the number of rows in the tables, so on and so forth, and we get this plan. It's the full table join we walked through a little bit earlier. And now all the estimates are pretty close to the actuals. All the number of rows we're getting from each table are bang on. Join estimates are slightly different, but only slightly. Like I say, if you're within an order of magnitude, then generally that is good enough. So we've managed to fix it here. So thing to look for, have you got missing or out of date statistics? Now, these days it's pretty rare you need to do this. For quite some time now, Oracle database by default has a background job which will gather stats for you. So it tends to be pretty rare that you need to do this. It's generally, if you're writing some kind of batch process or big data change where you're changing a large fraction of the rows. Probably one of the most common examples is if you're importing data into a staging table as part of the load process. First thing you do, truncate the stage table and then load all your data in. So you've just completely deleted everything and inserted everything. So there's going to be potentially a very big difference in the number of rows, the values within those rows from the last time we gathered stats. So after that, it does make sense to just gather stats immediately. So the rest of the process has got good up-to-date information. Similarly, you've got any other kind of batch background process where you're changing like 10% or more of the rows, gathering stats straight away does make sense, but it's fairly rare that you'll need to do this. Let's look at another problem with incorrect row estimates. And this is one where you might actually have to do something or might want to take some action yourself. So we've got two queries here. We're one query looking for red cylinders and another one looking for red prisms. Okay, and in both cases, the optimizer thinks it's going to get just 3 rows. How many rows does it actually get? Well, interesting. We get 8 red cylinders, but 0 red prisms. Okay, so why has it done that? Well, there's actually correlation between these columns. All the rows, all the red bricks are in fact cylinders, and all the cylinders are red. So there is a overlap in those. If we search for red, we'll get 8 rows. If we search for cylinder, we'll get 8 rows. Searching for red cylinders, we still get 8 rows. But the optimizer doesn't know that. It doesn't know there's a relationship between those columns. When it goes, okay, 1/3 of the values are red, 1/3 of the values are cylinders. I assume there's no relationship whatsoever between those. And it just kind of multiplies the probabilities together. It goes 1/3 times 1/3 is 1/9. So it decreases the row estimate by 1/3 compared to roughly what it should be. So we've largely underestimated. Also, there's no red prisms. So in this case, it kind of overestimates. It goes again, yeah, I think there's no relationship there. But there is in fact this relationship. And this is a fairly common thing you might get, particularly things like addresses, locations. All addresses in London are in the UK. All addresses in Amsterdam are in the Netherlands. We'll forget those cities in the US that have copied all our European names. But for the most part, there's a very large overlap between city name and country. So if you've got city equals Amsterdam and country equals Netherlands, adding country equals Netherlands generally knocks out very few extra rows. It's almost the same number of rows as you get for Amsterdam. So this is a fairly kind of common problem you might encounter. So anyone got any ideas how we might address this one? Any thoughts on how we can tell the optimizer there is in fact this relationship here between the two columns? Ooh, a histogram from Rod Denberg. Histograms can be useful, but that helps for an individual column. It's not going to help us to spot the relationship between two columns. Okay, there's something else we need to look at here. Compound index. Compound index would be useful in this query because, of course, we could read that to rather than scanning the table. But again, it doesn't necessarily directly help the optimizer know that there's a relationship between these. There we go. Judith, extended statistics. I'm going to struggle to keep saying statistics through this talk. So extended statistics. So this is where we can tell the optimizer more information about relationships between columns in a table. So we can do something like this: gather stats for columns and put some brackets around the columns that we believe or know have related values. It will then gather stats on those as a pair. It will say, yep, okay, I can see that all the red bricks are cylinders and all the cylinders are red bricks, and can use that information to get better row estimates. So we do that, oops, excuse me, and we can see we now got the bang on estimate for the red cylinders. Still overestimates slightly for the red prisms. The optimizer will should never estimate 0 rows for an operation, because that can lead to all sorts of interesting problems later on down the plan. So you quite often find it still overestimates slightly, but our higher estimate is now bang on. So this is something that the database doesn't do automatically, or at least not by default. You can enable it should you wish to, but by default, you would need to tell it about these kind of relationships. And there's other things where you might apply functions to columns. So in this case, we're looking for all the rows which are in uppercase red, and we just said there's 8 red rows in the table. So we expect the optimizer to tell us 8 rows, right? What does it think? Just 1 row. Okay. And the problem here is it just doesn't know what to do with this function here. It goes, well, how do I apply that? I've got no information about what uppering this column does to the results of the table. So again, we can also create extended statistics on expressions as well, such as uppercase, lowercase, adding values, multiplying them, and so on. And we can do this, and the optimizer will get bang on estimates as well. So in general, what you'd like to do is not apply functions to your columns. Makes the indexes easier to create, more optimizer more likely to use them. But it's not always possible to avoid this. In some cases, you're joining 2 columns, and you need to apply the expression, the function, to one of them for the join to work. So in those cases, again, applying extended stats can help those. Just to Rob's points on a histogram, this is another thing that can lead to incorrect estimates in rows. This is when you've got an uneven distribution in values. If you look at counting, we've got a row for every person in the world. There's a lot more rows for people in China than there is for people in the Netherlands, right? So there's an uneven distribution in the values. Histograms can help the database spot this. But like the stats gathering process, the database can identify this automatically based on column usage and data skew. So you tend not to need to go in and fiddle with this. It's more of a handle by exception when it gets problems. You might want to go in and start mucking around and fiddling a bit more, but generally if you just let it run and then add or remove histograms if it doesn't quite get it right. Okay, let's move on and look at another example. So now on, we'll assume the stats are all right, and it's estimating how many rows we're going to get. In this case, we've got inefficient access. So we've got 2 full table scans, but we're getting just 1 row from each of those tables. We are doing multiple IO operations to get that 1 row. Doesn't sound right, does it? We've got the ratio the wrong way round here. Really, you want 1 IO operation that gets you lots and lots of rows. You don't want to have one row that does lots and lots of I/O to get it. We've got things the wrong way around here. So what can we do about this? Come on, let's see in the chat. How can we resolve this? How can we get this query to do less work? So we're getting one row. We've got a full table scan on these. We don't want this. What could we do? What could we create to do less work in this situation?
Silence.
Silence. No takers for this one.
No takers.
Oh, index. Will. Yeah, there we go. Thank you, Wilfred. Yes. So that's what we want to do here. We can use an index. By using, we can create some indexes. Didn't create any indexes on my table. Silly me. And what that allows the database to do is find the rows we're looking for. Exactly. So full table scan, read every single row in the table, check if it matches your where clause. With an index range scan, on the other hand, search the index to find only those entries that match your search criteria, your where clause, and then only go to the table for those. So we're getting one row from each table, and we can see we've dropped the amount of work we're doing down here drastically. So we have to do one I/O to read the index, one I/O to actually get the row from the table, so 2 per table for a total of 4. So this can lead to a big reduction in work. So if you've got a situation where you're doing a lot more I/O than you are getting rows, then think maybe you're missing an index here. There's a good chance that that's possible. So what can we do here about that? All right, then, let's look at another situation. Repeating work, doing things more often than we needed to. Okay, so this is going back to that scalar subquery example. I said there was another clue in the plan that tells you you've got a scalar subquery. If you sent me this plan, I could probably guess that you've got a scalar subquery for a couple of reasons. First up, there's no join. But secondly, we're doing this full table scan of the bricks table 3 times. Interesting. So well, why are we doing that? Well, we're doing it once per row or value that we get from the colors table. Interesting. Okay. Full scanning a table 3 times doesn't sound very good here, does it? So what could we do here? Any ideas, thoughts, suggestions on how we can reduce the amount of work we do in this scenario? So we don't have to do 3 full table scans of the bricks table. Join, yes, thank you, Rob. Straight in there. So what we can do is rewrite the scalar subquery to a join, something like this. Exactly how you're going to write the join will depend on your tables and the data and so on. But if we do that, we can now get a plan that looks like this. We read each full scan each table just once. Now it's worth noting that the optimizer can do this rewrite for you in some cases. So if it's able to go, well, logically, this scalar subquery is exactly the same as a join, it will in fact end up with a plan a bit like this for you. It can only do that in some circumstances, though. In some cases, you will need to rewrite the query yourself to avoid this. It's also worth noting that sometimes a scalar subquery could be the right way to do this. If these are truly colossal tables, billions of rows in them, if we're joining them all, but only getting, say, the first 10, we've got a top n query, join all the rows, do a top n to get the count, then we've had to read all the rows in at least one, possibly both of the tables. Whereas if we did full scan of the colors and then just scan the bricks table for the rows we get from that, it might work out better, particularly if we have got an index on the table in the scalar subquery. So you won't always want to rewrite them, but often you'll want to rewrite scalar subqueries as joins. Okay, let's move on. Next problem. Okay, another scenario. This is where we are reading a lot of rows from the table, but the query returns very, very few. So this is what we've got here. We've got full scan of bricks and a group by, and that reads 100,000 rows. But the query only actually returns just 3 rows. So what's going on here? How have we ended up with this? Well, it's a query a bit like this. We're grouping by color and counting the rows or whatever is getting min and max values. This is a really common type of reporting query for kind of business metrics. Show me the total number and value of sales per day for the past week, or per month for the past year. The number of rows you input here could be colossal. You could have millions, billions of rows that you have to read, but the size of the result set is fixed. You know, if you're doing daily counts for a week, you're going to get a maximum of 7 rows in your results. If you're doing monthly counts for a year, you're going to get a maximum of 12 rows in your results. So you're reading huge volumes of data, but the query is guaranteed to return very, very few rows here. So what can we do here? Any thoughts or suggestions about how we can make this quicker? Give me a moment to think about that. Materialized view from Judith, yes. So essentially what we'd really like to do here, particularly if this is query that we do a lot, is pre-compute the results, okay? And the best way to do that is to create a materialized view. So what we do is create this materialized view. It stores the result of this query in a table. And then we've got enable query rewrite, provided the data in the materialized view matches the data in that we've got in the actual table itself, the database can go, oh, you're running this query that you've got in the materialized view. I will just swap in that materialized view automatically. So a bit like when you create an index, you don't need to do anything special, tell the optimizer to use it. It just goes, oh, this index helps me read the data quicker. I will use it. The database can do the same with a materialized view. Now, things are a bit more tricky and fiddly with materialized views. It won't just do it automatically. As we saw, we have to enable query rewrite to enable this swap in, but we also need to keep that materialized view up to date. Every time we make a change to that table, we also need to put that change in the materialized view, which means we need to make it fast refresh on commit. So there are lots of caveats and gotchas around that. So a bit more than we've really got time, or I've got the inclination to go through right now. But once you get a fast refresh on commit materialized view with query rewrite enabled, it can be really fantastic for these aggregation reporting queries, which read huge numbers of rows, but return very, very few. So if you can't do that, there's lots of other tricks and little things you can do as well to help materialize views. We can discuss those another day if you're interested. Alrighty then. So we've covered a lot of things here. Let's just finish up with a bit more of an interesting thing. Unrealistic requirements. So we saw there reading lots of rows, returning very few. We can use a materialized view to pre-compute the results. Every now and again, you get someone who has a question like this. We've got a query that reads 100 billion, 10 billion rows, and it's returning all 10 billion rows, and it takes me about 10 seconds. Can you get it done in 1 millisecond or microsecond or some other teeny fraction of time? And so, we're just reading gobs and gobs of data, returning it to the client, and they want it done like, instantly. At this point, you're just like, come on, you're tearing my hair out, like, kill me now. Some things are just not possible. Some things you need to take a step back and go, well, why the heck are you doing this? Why are you returning 10 billion rows to the client? Doesn't matter how much we tune that query or optimize it, it's still just going to take a while. I say, for me to go from my house over to the Netherlands, it's going to take a few hours at least. Traveling by conventional routes, train, plane, and so on, a few hours at best. Now, we might be able to get that down even faster. It's great to see you all in the Netherlands. I believe that Netherlands has got something like the highest concentration of ACEs per square kilometer of population. So the most ACEs per population to land size area of any country in the world, I believe. So, it's really important place for us to be there and me to come and see you. So maybe Larry's feeling really kind and he's going to charter me a helicopter from my house to go straight there and bring my journey time down drastically to maybe under an hour, right? You know, it's still going to take a while to actually get there. You also got the best aces, Rob says. Absolutely, definitely. But the thing is, you know, even if we managed, I charter a private jet or a helicopter that leaves from exactly outside my house and drops me exactly at, you know, the convention center where we meet in person, still going to take, you know, quite a while, probably about an hour. There's just no getting away from that. There's just no physical way for me to get from where I live right now to the Netherlands in 10 minutes, for example. It's just impossible, you know, laws of physics and all that. There are some things sometimes which, you know, you have to kind of step back and go, well, what are you trying to do here? Is this really plausible? Is it possible to do in any in a realistic time frame? And then go, well, do I need to travel? You know, I can be with you instantly by presenting from my house as I'm doing right now. Sometimes you need to think about how you can rework the problem and try and avoid doing the work. You know, when all else fails, come up with a different plan. All right then, so let's recap and look at what we can do. So we saw the process of walking through the plan. Start at the top, work down to the first unvisited leaf, unless it's a scalar subquery, go up to its parent and repeat the process. So you can follow that wiggly line through the plan. Once you know the route, how do we know whether to get a better plan? Well, first up, check the row estimates. Is the number of times this operation started multiplied by the number of rows the optimizer thought it would get, roughly equal to the number of rows we actually got? If it is, it's probably a good plan, or as good as we're going to get based on the data structures we have currently. If the query is still too slow when the estimates are good, then you've got to ask yourself, well, can we create faster access paths? Can we create indexes to speed things up? Can we create materialized views? You know, if we want really big performance gains, can we start looking at things like database in memory or partitioning to change things even further? How can we reduce the work we're doing to read those rows? So look at those. And at some point, you're just reading so much data and returning it so much, you've got to ask yourself, well, why are we doing this? How realistic is it to expect, you know, us to read 1 billion rows in a microsecond or something like that? Some things are just unachievable or very difficult to achieve, at least not without spending huge sums on hardware. Okay, so hope you found this useful. Let's look. So where do you go from here? This is just kind of give you a taster of some of the ideas, some of the things you want to look at. So a few things you might want to follow up on. First up, a bit more detail on getting a plan. So I showed you a very quick snapshot of how to use DBMS Xplan. A whole bunch of other tools and resources you can use to do that. I mentioned Autotrace and SQL Developer. I really like that. There's great little graphical things so you can expand and collapse things. Makes it much easier to spot those parent-child relationships in complex plans. Also, things like the SQL Monitor. So if you're licensed for diagnostics and tuning, long-running queries, it automatically captures details of those in real time in the SQL Monitor. So you can see how the plan is progressing in real time. Very useful. It's very useful to help you learn about how the database processes queries, even if you're not actually trying to actively tune one, because you can see as it ticks through which operations start at which point and so on. So very useful even if you're not actually trying to tune a query. But as I said, do need to be licensed for diagnostics tuning there. Finally, a SQL trace. This is where you enable a trace in a session and it captures details about the execution for all the queries in that session until you stop or disconnect. You can then format that with tkprof or again load it in SQL Developer, and you can see the plans for each query, how long it took. Very useful if you've got a big long process with lots of different SQL statements in. You can like, oh, which of these is the slowest? So very useful there. So great resource. But if you want to get the scripts from this presentation, you can head to this live SQL link. I haven't included quite all the query examples, but you can get the data, the tables, and the first several examples there. Finally, I've recently been launching a whole bunch of videos, databases for developers performance, on my YouTube videos. I've got the playlist there where similar stuff talked about today, but I go into much more detail in a lot of these topics. I've also got a free performance tuning course based around those videos coming on the Oracle Dev Gym very, very soon, so stay tuned for that. Alrighty then, I think that's kind of about all I had. So any questions or comments before we finish up? Okay, so okay, thanks.
Give
okay,
people
thank you
time
for
to
all
type.
Hmm?
Give people some time to type.
Yeah, give people some
Except
time
for
to type.
thanks.
Yes. Yeah, if you've got questions, just feel free to reach out to me. You know, there's always asktom@oracle.com, or you can reach out to me on Twitter. Patrick's got my details as well. If you know.
There is a question in the Q&A.
Oh yeah.
How to get the right join method?
How to get the right join method? Okay. So that's an interesting question. So, like I say, when it comes to in a plan things to tweak, there's basically two things you can do. You can look at tweaking the stats, or you can create indexes, materialized views, and so on. And so that's first, probably the biggest thing to look at is what are the stats. So the optimizer prefers to start with the table that returns the fewest rows. So the first table on the join should be the one that has the least rows. If it's not, then you'll probably want to look at stats and see what you can do there. Worth bearing in mind, from 12C, the optimizer has something called adaptive plans. So this is one plan where it considers two possible ways of joining tables. So it goes, well, I'm not sure if nested loops is better or hash joins are better. So what I'll do is I'll just try both, right? Or I'll consider both. And the first time we execute the query, it'll look at the number of rows coming out of that first table, and then choose hash join or nested loop based on that. If you want to know more, I do talk about this quite a bit more in that video series I've got linked up there. So it's video 7 or 8. It's called How Joins Work. So if you look there, there's a lot more information about how the joins work when one join is the right or the other. But generally, look at improving the stats or changing the indexes and so on. Alrighty then.
And there's another question. Does gather table stats have impact on users using the tables at hand?
So you mean other queries going on and so on at the same time? In general, stats are pretty, we're as light touch as we can be. We've got more and more efficient at gathering these as time has gone on. Generally speaking, hopefully you shouldn't notice too much of an impact. I know in older versions it could be. If you are spotting problems with this, then it's probably something you want to start talking to support about, particularly if you're on more recent versions. But you know, it's not something I've noticed too many issues with recently. Rob, I hope you'll join us live again soon. Yes, I hope I do too. I'm not sure when that will be, but maybe we'll be there. Hopefully not too long. See, D. Louisville. There's a situation where we have a view with 20+ joins and the performance is deteriorating. Could we use the explain plan to improve this alternatives for a whole lot of joins? So, so what you want to do, as I say, is get that execution plan and look at how many rows, you know, what's happening in there. And if you say performance is deteriorating, it suggests probably it was okay at some point. Few possible reasons it might now be getting slower. Either you are just generally processing more data. You know, day 1, there's very little data, so everything's fast. Day 100, there's more, things start to slow down a bit, in which case you might need to rethink how it's actually being processed. If that's not the case, you know, if it's still processing relatively few rows, then they say, look at the stats. Maybe the stats have gone slightly out of date. see what you can do there. You can create materialized views to pre-compute joins. So that can be useful in some cases. So if you've got 20 tables, create materialized view which calculates all the join for you can be a big saver. It's not quite as easy to use or implement as like the group by queries we saw a minute ago, but that's something to look at. If you've got more particular questions, if you've got an example of the execution plan and you want us to walk us through that, then reach out and we can discuss it, see what you can do to help you there. Okay. How are we doing? We've got about 5 minutes left. Shall we?
Yeah.
Shall we? Okay. Alrighty then.
Nothing more.
Nothing more for now. So it's as always, it's been great. It's sad that I'm not able to see you in person, as Rob says. Hopefully, I'm pretty sure it'll be at least next year before we can meet again, so to speak. But hopefully we will. In the meantime, I really hope this has been enjoyable for you. But more importantly, I hope you learned something. Go out and improve. Start the journey for tuning SQL. All right.